Recall that if A is any non-empty set and S sub A is the set of permutations of A, then the set S sub A forms a group under permutation multiplication. So now I want to ask, what if A is the set 1, 2, 3, all the way up to n? So it's a finite set. Well, if A is the finite set, 1, 2, 3, all the way up to n, then the group S sub n consisting of all the permutations of A under permutation multiplication is called the symmetric group of degree n. The order of a group G, which we denote with what looks like little absolute value bars, is the number of elements in the group. So I want to point out that we said that S sub n was the symmetric group of degree n, but that doesn't mean that the order of S sub n is n. So what is the order of S sub n? Well, let's think about this. Suppose we have an example here of an element that might be in S sub n, so I'll call it phi. So what would phi look like? So phi would be some permutation, and would have elements 1, 2, 3, and then all the way up to, well, we'd have n minus 1, and then eventually n. And so what would happen to 1? Well, that would be phi of 1. It would take 1 to whatever phi of 1 is. 2 would go to phi of 2. 3 would go to phi of 3, and so on. So you can see how this works. So this is just some notation here. So let's use this idea to try and figure out what the order of S sub n would be. And let's look at the first option here, phi of 1. Where could we take 1? How many options, how many choices do we have for phi of 1? Well, if there's n things here, we could have n choices. We could have phi of 1 be 1, or phi of 1 be 2, or phi of 1 be 3, all the way up to n. So we would have n choices for phi of 1. Now, if we've made a choice for phi of 1, then we have n minus 1 choices left for phi of 2. So I'll multiply that here, so n minus 1. And then how about for phi of 3? Well, I already used up 2 of the choices here, so I would have n minus 2. And you can keep going with this idea here until you get to phi of n minus 1. And by that point, well, there's only 2 choices left for phi of n minus 1. And then finally, phi of n, there's only 1 choice left. And so this represents the order of the symmetric group S sub n. And you might recognize this. This is just n factorial. And I think we saw this before, and it kind of makes sense. If you think about a group of 3 elements, for example, 1, 2, and 3, there would be 3 factorial or 6 different ways of arranging them, and we've seen this before. So in general, the degree of the symmetric group S sub n is n, but the order of the symmetric group S sub n is n factorial. So you might recall that we had the group S sub 3, which was the symmetries of an equilateral triangle. And it had these elements, rho naught, which was the identity, and then rho 1, which was a rotation, rho 2, which was another rotation, and then the mu's, mu 1, mu 2, mu 3, which were flips. So here are the elements. And if we look at these, we see that so the identity just leaves everything alone. Rho 1 kind of rotates everything once around. Rho 2 rotates everything again once around. Mu 1 leaves 1 alone and flips 2 and 3. So it kind of flips across the axis running through bisecting that angle at 1 there. And then similarly for mu 2 and mu 3. So the notation here, S sub 3, suggests that maybe this might be a symmetric group. And if we think about 1, 2, and 3 as being the elements in that set that we talked about earlier, then you can see how we might have permutations of this set. So here are the elements written out again, and for each one of these elements that we earlier had identified as a symmetry of an equilateral triangle, let's try and write it in permutation notation. Okay, so the first one was the identity. So for the identity, that would be rho naught, we will write it as, well, we have 1, 2, and 3, and the identity would leave everything alone. So that kind of makes sense. How about row 1? That was the rotation. So we start with the 1, 2, and 3 up top, and now we ask, okay, what happened to each of these things? So where did 1 go? Well, 1 went to where 2 was. You see now it's where the 2 was before. So 1 went to where 2 was. 2 went to where 3 was. And 3 went to where 1 was. Row 2, that's another rotation. So I have 1, 2, and 3. And now I think you can see that 1 went to where 3 was. See, there's the 1 up there. So 1 went to where 3 was, 2 went to where 1 was, and 3 went to where 2 was. For mu1, this was a flip, and the flip left 1 alone. If you look at the triangles here, 1 stayed exactly where it was, so I can just put a 1 here, and it was the 2 and the 3 that flipped. So 2 went to 3, and 3 went to 2. For mu2, that's the one that left 2 all alone. So 2 stayed where it was, 1 went to 3, and 3 went to 1. And then finally, mu sub 3 was the one that left 3 all alone. And so 3 stayed where it was, and 1 and 2 switched places. Okay, let's look at an example calculation. We saw before that row 1 times mu2 equaled mu1. And so I explored this in an earlier video. You can actually see how this works out with the symmetries of an equilateral triangle. Just to kind of quickly recap, here are the 3 things we're talking about here. And remember how this works with function composition, because that's really what this is. We actually go in reverse order. So when I have row 1 mu2, you actually apply mu2 first. So mu2 says take 1 and move it up here, take 3, move it down here, and take 2 and leave it exactly where it is, and then apply row 1 to that. And if you watch the earlier video, I work through this in terms of this notation, but in this video, I want to look at permutation notation. So underneath each of these, I'm going to write the equivalent permutation notation and then apply the permutation multiplication to see if we do get the right answer. Okay, so row 1 that before we said was, if I take the 1, 2, 3 here, row 1 was the one that sent 1 to 2, 2 to 3, and 3 to 1. Mu2 was the thing that left 2 alone and swapped 1 and 3. And we need to check and make sure that we get mu1 when we do this. So let's write these out, and I'll write them next to each other so we can apply the permutation multiplication. And so remember, again, you work in reverse order. So let's write out what we think we should get here. Okay, so 1 goes to 3 and 3 goes to 1. That means 1 stayed where it was. 2 stayed at 2, but then 2 was brought to 3. So 2 goes to 3. 3 was brought to 1. 1 was brought to 2. So overall, 3 was brought to 2. And if we look at this, yep, this is the thing that leaves 1 alone, that is mu1. So this does indeed work. So now maybe you might be asking, if S3 represents the symmetries of an equilateral triangle, does S4 represent the symmetries of a square? Well, remember the symmetries of a square we represented with D4. And so we have our rotations, rows, we have mu's, and then we also had our deltas, and so here they are listed out. The rows make sense, you're just kind of rotating everything around. The mu1 is a flip, and if you look at it, it's a flip across a axis down the middle. So it kind of is like a vertical axis dividing the square in half, and so it flips everything over to the other side. And the mu2 is the axis that divides the square in half through the center horizontally and flips everything. And the deltas were the ones that flipped across the diagonal. If you notice, the 4 and 2 stay where they are, but the 1 and 3 swap places for delta 1. And for delta 2, it's kind of the opposite way, where the 1 and 3 stay where they are, and the 2 and the 4 swap places. So D4 has 8 elements. But what about S4? S4, remember how this works. The order is 4 factorial, or 24. So already we see, no, this can't be right. The symmetries of a square, well, there's only 8 of them, and S4 has 24 elements. But we can say that D4, in a sense, is a subgroup of S4. Now remember that D4 is really referring to the symmetries on a square, and S4 is referring to permutations of the set 1, 2, 3, 4. So we have to be a little bit careful because it's not quite accurate to say it's a subgroup. I'm cheating a little bit because there are different ways of thinking about them. But if we think of the elements of D4 as permutations on the set 1, 2, 3, and 4, then we see that D4 can be thought of as a subgroup of S4. Remember, that's when we think of it in that way. And remember the notation, when we say something is a subgroup of something else, we use what looks like a greater than or less than sign, in this case less than, since D4 is a subgroup of S4 when you think of D4 as permutations on the set 1, 2, 3, and 4.